Look up at the night sky. Go ahead, I'll wait. See those stars? Those tiny pinpricks of light that humanity has gazed at for millennia, wondering what's out there. Every single one of those stars could fit inside what we're about to discuss. Multiple times. In fact, the entire observable universe, everything we've ever seen, measured, or detected, might be nothing more than a microscopic speck compared to what actually exists. And here's the thing that should absolutely blow your mind. We just figured this out. Like, really recently. Scientists have been gathering evidence that fundamentally changes our understanding of cosmic scale. And what they've discovered is so incomprehensibly massive that it makes our previous understanding of the universe look like we were measuring the ocean with a teaspoon. You think you understand big? You don't. Nobody does. The human brain literally isn't wired to comprehend the scales we're about to explore. But we're going to try anyway, because what scientists have recently discovered about the true size of the universe is perhaps the most mind-bending revelation in the history of astronomy. So buckle up. We're about to take a journey from the scale of atoms to structures so large that light, traveling at 300,000 kilometers per second, takes billions upon billions of years to cross them. We're going to explore recent discoveries that suggest our universe might be infinitely larger than we ever imagined. And by the end of this video, your perspective on existence itself will be fundamentally altered. Let's start with what we thought we knew. Part 1. The Cosmic Measuring Tape. Chapter 1. How we measure the impossible. Here's a fun question. How do you measure something you can't touch, can't reach, and can barely see? Because that's the fundamental problem astronomers have faced for centuries. You can't exactly pull out a ruler and measure the distance to a star. For most of human history, we had absolutely no idea how big the universe was. Ancient civilizations thought the stars were holes in a celestial sphere, maybe a few thousand miles up. Even brilliant minds like Aristotle got it catastrophically wrong, believing the entire cosmos was maybe a few million miles across at most. The first person to actually nail down cosmic distances was a woman named Henrietta Swan Leavitt in 1912, and her story is criminally undertold. Working at Harvard Observatory as a computer, literally, that was the job title for women who did calculations that male astronomers couldn't be bothered with. Leavitt discovered something extraordinary about certain stars called Cepheid variables. These stars pulse. They get brighter and dimmer in a regular, predictable pattern. And Leavitt noticed that the period of their pulsation, how long it takes them to complete one bright dim cycle, is directly related to their actual brightness. This is huge. Because if you know how bright something actually is, and you can measure how bright it appears to be, you can calculate exactly how far away it is. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb and it looks dim to you, you can calculate how far away it must be to appear that dim. Leavitt had just given astronomers a cosmic light bulb they could use as a measuring stick. Using Leavitt's discovery, astronomers started measuring distances to nearby galaxies. And this is where things got weird fast. In 1929, Edwin Hubble, yes, the telescope guy, made an observation that would shatter our understanding of the cosmos. He noticed that distant galaxies weren't just sitting there. They were moving away from us, all of them. And not just moving, The farther away a galaxy was, the faster it was receding. It was as if the entire universe was expanding, carrying galaxies apart like raisins in rising bread dough. This was insane. The universe wasn't static and eternal like everyone assumed. It was growing. And if it's growing now, that means it was smaller in the past. Rewind far enough, and everything, all matter, all energy, all of space itself, was compressed into an infinitesimally small point. The Big Bang wasn't an explosion in space. It was an explosion of space. Space itself began expanding, and it's still expanding right now, carrying galaxies away from each other at ever-increasing speeds. But here's where the measuring gets tricky. To understand how big the universe really is, we need to talk about the observable universe versus the actual universe. And trust me, the difference is staggering. Chapter 2. The observable universe, what we can see. The observable universe is everything we can see from Earth. Every star, every galaxy, every photon of light that's had enough time to reach us since the Big Bang began. And it's enormous. Current measurements put the observable universe at about 93 billion light-years in diameter. Let that sink in for a second. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. The observable universe is 93 billion of those. In kilometers, that's a number with 26 digits. Your brain can't process that. Neither can mine. But wait, you might be thinking, if the universe is only 13.8 billion years old, how can we see things 46.5 billion light-years away in any direction? Shouldn't the observable universe be only 27.6 billion light-years across at most? Great question. Here's the mind bender. Space itself has been expanding this whole time. So light that was emitted from a galaxy 13 billion years ago didn't just travel 13 billion light-years. While that light was traveling toward us, the space between us and that galaxy was expanding, stretching out the distance. By the time the light reaches us, that galaxy is now 46 billion light-years away. It's like running on a treadmill that's accelerating away from you. Even though you're running forward, you're actually getting farther from where you started because the ground beneath you is moving. So the observable universe, this sphere of everything we can possibly see, is 93 billion light-years across. Within this sphere, there are roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star might have planets. The numbers become meaningless almost immediately. The Milky Way, our home galaxy, contains somewhere between 100 and 400 billion stars. It's about 100,000 light-years across. Our Sun is an average, unremarkable star, about 2/3 of the way out from the galactic center. Earth orbits this average star at a distance of 150 million kilometers, a distance we call 1 astronomical unit, or AU. Just to reach the nearest star to our Sun, Proxima Centauri, 4.24 light-years away, would take our fastest spacecraft about 70,000 years. To cross our galaxy would take 100,000 years at light speed. To reach the edge of the observable universe would take 46.5 billion years at light speed. These scales break our intuition. They're too big to visualize, too vast to truly comprehend. And yet, this is just what we can observe. Recent discoveries suggest that what we can see might be an infinitesimally small fraction of what actually exists. Chapter 3. The Cosmic Horizon. Here's something that will mess with your head. There are parts of the universe we will never, ever be able to see. Not because they don't exist, but because the universe is expanding so fast that light from those regions will never reach us. Imagine you're on a beach, and every second the beach extends by a meter in all directions. You start running toward the ocean at 1 meter per second. Can you ever reach the water? No, because the water is receding faster than you can run. Light faces the same problem with the expanding universe. This creates what's called the cosmic event horizon, the boundary beyond which events cannot affect us, because the space between us is expanding faster than light can cross it. And this horizon is getting closer. Paradoxically, as time goes on, we'll be able to see less of the universe, not more. This is because of dark energy, the mysterious force causing the universe's expansion to accelerate. Discovered in 1998 by 2 teams of astronomers studying distant supernovae, dark energy is one of the biggest mysteries in physics. We don't know what it is. We just know it's pushing the universe apart faster and faster. Current measurements suggest dark energy makes up about 68% of the universe. Dark matter, another mysterious substance we can't see but can detect through gravity, makes up about 27%. The normal matter that makes up stars, planets, and us? About 5%. We're literally the minority component of our own universe, and we don't understand 95% of what the cosmos is made of. But here's what recent observations have revealed. Dark energy isn't just accelerating expansion. It's doing so in a way that suggests the universe might be much, much larger than just the observable sphere we can see. In fact, it might be infinite. And when scientists say infinite, they don't mean really big. They mean actually mathematically infinite, no edge, no boundary, extending forever in all directions. How do we know this? The answer lies in something called cosmic curvature. Chapter 4, The Shape of Everything. Imagine you're an ant on a surface. Depending on the shape of that surface, your universe behaves very differently. If you're on a flat plane, you could walk forever in one direction and never come back to where you started. If you're on a sphere, you'd eventually loop back. If you're on a saddle-shaped surface, parallel lines would diverge. The same is true for our universe in 3 dimensions. The geometry of space itself determines its ultimate fate and size. And recent measurements from satellites like WMAP and Planck have been measuring this curvature with unprecedented precision. The result? The universe appears to be flat. Not flat like a pancake, that's just a 2-dimensional analogy. Flat in the geometric sense, meaning that parallel lines stay parallel, and the angles of triangles add up to 180 degrees, even over cosmic distances. This flatness is measured by something called omega, which represents the density of the universe compared to the critical density needed to be perfectly flat. Recent measurements put omega at 1.00 plus or minus 0.02. In other words, the universe is flat to within 2% accuracy. Now here's where it gets wild. If the universe is truly flat, and our measurements suggest it is, then it's most likely infinite in size. Not just really big, actually infinite, extending forever. Think about it. If the universe is curved like a sphere, it could be finite but unbounded. You could travel forever and loop back, but there's a maximum volume. If it's saddle-shaped, negatively curved, it's definitely infinite. But if it's flat? An infinite flat universe is the simplest solution mathematically. This means that beyond our observable universe, beyond that 93 billion light-year sphere, we can see there's more universe, probably infinitely more, with infinitely more galaxies, stars, and planets. In fact, if the universe is truly infinite and matter is distributed roughly uniformly throughout it, then somewhere out there, there's another Earth. Actually, there are infinitely many other Earths, with infinitely many versions of you, reading infinitely many versions of this script. This isn't science fiction. This is a serious consequence of an infinite universe with quantum mechanics. In an infinite universe, every possible configuration of matter that can exist will exist somewhere, repeated infinitely many times. Your exact duplicate, same atoms, same memories, same everything, exists somewhere out there, about 10 to the power of 10 to the power of 29 meters away, give or take. That number is so large, it makes 93 billion light years look like nothing. But we're just getting started on understanding cosmic scale. Chapter 5, Structures Beyond Imagination. Let's talk about the largest things in the universe. Not individual objects, but structures, cosmic architecture built over billions of years by gravity and dark matter. The largest individual objects are galaxy superclusters. These are collections of galaxy clusters, which themselves are collections of galaxies. Our Milky Way is part of the local group, a small collection of about 54 galaxies. The local group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters. But even the Virgo supercluster is tiny compared to what we've discovered. In 2014, astronomers identified the Laniakea supercluster, a structure containing 100,000 galaxies spread across 520 million light-years. Our entire local group is just a tiny suburb on the outskirts of Laniakea. And Laniakea isn't alone. It's connected to other superclusters through massive filaments of galaxies, cosmic strands along which matter has been pulled by gravity over billions of years. Between these filaments are vast cosmic voids, regions of space with almost no galaxies, stretching hundreds of millions of light-years across. The structure of the universe at the largest scales looks like a cosmic web, filaments and walls surrounding enormous voids, creating a soap bubble-like structure that extends in all directions. The largest individual structure we've found is the Hercules Corona Borealis Great Wall, a galactic filament stretching more than 10 billion light-years across. To put that in perspective, light would take 10 billion years to cross it. When the light we see from one end of this structure began its journey, the universe was only about 3.8 billion years old. These structures are so large, they challenge our understanding of how the universe formed. According to the cosmological principle, the idea that the universe is roughly the same everywhere, there should be a maximum size to structures based on how long matter has had to clump together since the Big Bang. Structures like the Hercules Corona Borealis Great Wall are right at or possibly beyond this theoretical limit. Their existence suggests either our models of cosmic evolution need adjustment, or there's something about the universe's early conditions we don't understand. But even these incomprehensibly large structures might be small compared to recent theoretical predictions about the universe's true scale. Chapter 6: Inflation and the Multiverse. In 1980, physicist Alan Guth proposed a theory that would revolutionize cosmology: cosmic inflation. The idea is that in the first fraction of a second after the Big Bang, we're talking 10 to the power of minus 36 seconds here, the universe underwent a period of exponential expansion, growing from subatomic size to roughly the size of a grapefruit almost instantaneously. This inflation solved several problems in cosmology, like why the universe appears so uniform in all directions and why it's so flat. But it created a new one. If inflation happened once, it probably happened many times. And if it happened many times, our observable universe might be just one bubble in an eternally inflating cosmic foam. This is the theory of eternal inflation, and its implications are staggering. According to this model, what we call the universe, our observable bubble of space-time, is just one of countless bubble universes being continuously spawned by the inflation process. Each bubble could have different physical laws, different constants, different properties entirely. Some bubbles might have no stars, some might have only black holes, some might be filled with exotic forms of matter we can't even imagine. And our bubble, with its particular set of physical laws that allow stars, planets, and life, is just one possibility among infinite others. The multiverse isn't just speculation anymore. It's a serious prediction of our best theories of cosmic inflation, supported by astronomical observations and theoretical physics. Multiple research teams have been searching for signs that our bubble might have collided with another in the distant past, which would show up as anomalies in the cosmic microwave background radiation. So far, no confirmed collisions. But the search continues. If the multiverse theory is correct, then the true size of the universe becomes a meaningless question. There is no edge, no boundary, no total size. Just infinite bubbles forming in infinite space for infinite time. Our observable universe, that 93 billion light-year sphere, becomes less than a grain of sand on an infinite beach that extends in dimensions we can't even perceive. Part 2: Breaking the Cosmic Speed Limit. Chapter 7: The Problem with Infinity. Okay, so we've established that the universe might be infinite. Cool. Except that creates some absolutely wild problems that scientists are only now beginning to grapple with. First, let's talk about what infinity actually means. When mathematicians say something is infinite, they're not saying it's just really, really big. They're saying it has no end, no boundary, no limit whatsoever. And when you start applying infinity to physical reality, things get weird fast. If the universe is truly infinite, and matter is distributed roughly evenly throughout it, which our observations suggest it is, then there are infinite galaxies, infinite stars, infinite planets. And here's where your brain should start hurting: infinite copies of Earth. This isn't speculation, this is math. In an infinite universe with quantum mechanics, every possible arrangement of particles will occur somewhere. Not just once, infinitely many times. There's a version of Earth where dinosaurs never went extinct. There's a version where you're the president. There's a version where the Roman Empire never fell. There's a version where humans never evolved. There's a version identical to ours, except one atom in a random rock in Australia is positioned slightly differently. All of these exist. Right now, somewhere in the infinite expanse beyond our cosmic horizon. But it gets weirder. The physicist Max Tegmark calculated that your nearest identical copy, a person with your exact atomic configuration, memories, and life history, exists about 10 to the power of 29 meters away. That's a 1 followed by 10 billion zeros meters. For comparison, the observable universe is only about 10 to the power of 26 meters across. Your doppelganger is incomprehensibly far away, in a region of space we can never see, living a life identical to yours in every way because they literally are you, just made of different atoms. And there are infinitely many of them, infinitely many yous, spread throughout infinite space, all reading this script, all having the same thoughts you're having right now. This is called the quantum Xerox problem, and it's one of the strangest implications of an infinite universe. It doesn't violate any laws of physics. It's just a consequence of probability meeting infinity. But here's what keeps cosmologists up at night. We can't prove any of this. By definition, these duplicate universes are beyond our cosmic horizon. We can never observe them, never interact with them, never confirm they exist. They're physically real, if our theories are correct, but forever inaccessible. This raises a philosophical question. If something exists but can never be observed or interacted with in any way, does it meaningfully exist? Science usually deals with testable predictions, but infinity gives us predictions we can never test. Chapter 8: Recent Discoveries That Changed Everything. Let's get back to observable science, because in the last decade, several discoveries have fundamentally altered our understanding of cosmic scale, and most people have no idea this revolution even happened. In 2013, the Planck satellite completed the most detailed map ever made of the cosmic microwave background, the afterglow of the Big Bang. This radiation has been traveling through space for 13.8 billion years, and it contains information about the universe's earliest moments encoded in tiny temperature variations. By analyzing these variations, scientists can determine the universe's age, composition, and geometry with incredible precision. And what Planck found was shocking. The universe is even flatter than we thought. The curvature parameter is now measured to be 0.0007 plus or minus 0.0019. That means if the universe is curved at all, the radius of curvature is at least 400 times larger than the observable universe. In practical terms, the universe is so flat that it's almost certainly infinite. But Planck found something else: anomalies in the cosmic microwave background that shouldn't be there. There's a cold spot, a region of space that's significantly cooler than it should be. There are unexpected alignments in the temperature variations that seem to violate the cosmological principle. Some scientists think these anomalies might be evidence of other universes, that our bubble universe collided with another in the distant past, leaving a bruise in the cosmic microwave background. Others think they're just statistical flukes. The debate continues, but the possibility alone is revolutionary. In 2019, another discovery rocked cosmology: the Hubble constant crisis. The Hubble constant measures how fast the universe is expanding, and here's the problem. We get different values depending on how we measure it. When we measure expansion using the cosmic microwave background, we get one number, about 67 kilometers per second per megaparsec. When we measure it using nearby supernova and Cepheid variables, we get a different number, about 74 kilometers per second per megaparsec. This doesn't sound like a big difference, but it is. These measurements should agree. They're measuring the same thing. The fact that they don't suggests either our measurements are wrong or our understanding of cosmic evolution is incomplete. Some physicists think this discrepancy might indicate that dark energy isn't constant, that it's changed over cosmic history. Others think it might be evidence that the universe is more complex than our models assume, possibly with different expansion rates in different regions. If the expansion rate varies by location, that would have massive implications for the universe's size and structure. It could mean the universe is even larger and more complex than infinity would suggest. Then in 2020, astronomers discovered the South Pole Wall, a massive cosmic structure containing thousands of galaxies, stretching 1.4 billion light-years across. What's remarkable isn't just its size, but the fact that we only just noticed it. This structure has been hiding in the zone of avoidance, a region of the sky obscured by our own galaxy. The South Pole Wall's discovery suggests we might be missing other enormous structures simply because we can't see through the dust and stars of the Milky Way. Our maps of the universe are incomplete, and we don't know what else might be hiding in the blind spots. Chapter 9: Dark Flow and the Great Attractor. Here's something that shouldn't exist according to our models: dark flow. In 2008, astronomers noticed something bizarre. Galaxy clusters in a particular region of the sky are moving in a coordinated direction at about 600 kilometers per second, far faster than they should be based on local gravitational influences. It's as if something outside our observable universe is pulling on these galaxies. Something with an unimaginable gravitational field tugging on matter from beyond the cosmic horizon. This phenomenon is called dark flow, and it's controversial. Some scientists think it's a measurement error. Others think it might be evidence of structure beyond the observable universe, massive concentrations of matter that we can't see but whose gravity we can detect. If dark flow is real, it tells us something profound. The observable universe isn't isolated. It's influenced by what lies beyond our cosmic horizon. The infinity beyond is not just theoretical. It's actively affecting what we can observe. Related to this is the Great Attractor, a gravitational anomaly discovered in the 1970s. Our galaxy, along with hundreds of thousands of others, is being pulled toward a region of space in the direction of the constellation Centaurus. For decades, we couldn't see what was pulling us because it's hidden behind the Milky Way. But modern telescopes using X-ray and infrared light, which can penetrate galactic dust, have finally revealed the culprit: the Norma cluster, part of the larger Laniakea supercluster. But even this doesn't fully explain the motion. Our galaxy is moving toward the Great Attractor at about 600 kilometers per second, but the Great Attractor itself is moving toward something else: the Shapley supercluster, an enormous concentration of galaxies about 650 million light-years away. And the Shapley supercluster? It's being influenced by structures even farther away. It's turtles all the way down, or in this case, gravitational influences all the way out to the cosmic horizon and possibly beyond. These discoveries suggest the universe's structure is more complex and interconnected than we realized. Matter isn't randomly distributed. It's organized into hierarchies of structure, extending to the largest scales we can measure, and probably beyond. Chapter 10: Quantum Mechanics Meets Cosmic Scale. Now, let's talk about something that will absolutely melt your brain. What happens when you apply quantum mechanics to the entire universe? Quantum mechanics, the physics of the very small, tells us that particles exist in multiple states simultaneously until observed. Schrödinger's cat is both alive and dead until you open the box. Electrons are in multiple places at once until measured. This is weird enough at small scales. But what happens when you scale it up to the entire universe? According to the many worlds interpretation of quantum mechanics, every quantum event causes the universe to split into multiple branches, each representing a different outcome. Every time a particle could go left or right, the universe splits into two versions, one where it went left, one where it went right. This happens countless times per second for every particle in the universe. The result? An infinite multiverse of branching timelines, each one as real as the others, each one containing a different version of history. In one branch, you decided to keep reading this script. In another, you clicked away. In another, YouTube never existed. In another, humans never evolved. Every possibility plays out in some branch of the multiverse. Now combine this with cosmic inflation. We've got bubble universes from eternal, inflation, each potentially infinite in size, each containing infinite copies of everything due to quantum probability, and each bubble containing infinite branching timelines from quantum mechanics. Infinity multiplied by infinity, multiplied by infinity. The total scope of existence becomes literally incomprehensible. And here's the kicker. All of this might be just one level of an even larger hierarchy. Physicist Max Tegmark proposed a 4-level multiverse hierarchy. Level 1, other regions of our infinite universe beyond our cosmic horizon, the infinite Earths we talked about earlier. Level 2, other bubble universes from cosmic inflation, each with potentially different physical constants and laws. Level 3, the many worlds interpretation branches where every quantum possibility exists. Level 4, mathematical universe hypothesis, every mathematically consistent structure exists as a physical reality. Not just universes with different laws, but universes with entirely different mathematical foundations. Level 4 is wild. It suggests that every possible mathematical structure, every conceivable set of logical rules, exists as a physical universe somewhere in a meta-multiverse beyond comprehension. There's a universe where 2 + 2 = 5, and physics works on entirely different mathematical principles. There's a universe with 17 spatial dimensions and no time. There's a universe where consciousness is the fundamental building block rather than matter. All of these exist, not as abstract concepts, but as actual physical realities. If Tegmark is right, is he right? We don't know. We might never know. But the math is consistent, and several aspects of his hypothesis make testable predictions about our own universe. Chapter 11, the holographic principle. Let's take a left turn into one of the strangest ideas in modern physics. What if the universe isn't actually three-dimensional? The holographic principle, developed by physicists Gerard 't Hooft and Leonard Susskind, suggests that all the information contained in a volume of space can be described by information on the boundary of that space. Think of it this way. A hologram is a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. The holographic principle suggests our three-dimensional universe might be the same thing, a projection from information encoded on a two-dimensional surface. Where is this surface? At the cosmic horizon. All the information about everything in our observable universe, every particle, every force, every event, could be encoded on the spherical boundary of the observable universe, and our three-dimensional experience is a projection of that information. This sounds like crazy metaphysics, but it's actually based on solid physics, particularly black hole thermodynamics. Stephen Hawking proved that black holes have entropy, a measure of information, and that this entropy is proportional to the surface area of the event horizon, not the volume. This was bizarre. Entropy should be proportional to volume. There should be more information in a bigger space. But for black holes, information is limited by surface area. This led physicists to suspect that space itself might work this way. The amount of information in any region of space is limited by the surface area of that region, not its volume. Our universe might be a hologram. If this is true, then asking about the size of the universe becomes even stranger. The universe could be infinite in its three-dimensional projection, while being finite in its fundamental two-dimensional encoding. Recent work in string theory, particularly the ADS/CFT correspondence, has provided mathematical evidence that the holographic principle might be correct. In certain theoretical models, a five-dimensional universe with gravity is mathematically equivalent to a four-dimensional universe without gravity, but with different forces. Neither description is more real than the other. They're different ways of encoding the same information. Reality might not have an intrinsic dimensionality at all. And if we live in a hologram, what does that mean for cosmic scale? Well, the true size of the universe might be measured not in light years, but in bits of information. And information capacity increases with surface area, not volume. In a holographic universe, expanding into larger space doesn't actually give you more room for information unless the boundary expands. This could explain why the universe is expanding. It's literally creating more information capacity by increasing the area of the cosmic horizon. Mind-bending? Absolutely. But multiple lines of evidence from quantum mechanics, general relativity, and string theory all point toward holography being a fundamental principle of reality. Chapter 12. What lies beyond the cosmic horizon? Let's get really speculative. What actually exists beyond the edge of the observable universe? We've talked about infinite space with infinite galaxies. We've talked about bubble universes and quantum branches. But here's something most people don't realize. The cosmic horizon is moving. As time passes and the universe continues expanding, more distant regions of space cross into our observable sphere. Light that was previously too far away to reach us finally arrives. We see new galaxies appearing at the edge of our vision, emerging from beyond the horizon like ships appearing over the ocean. But simultaneously, galaxies at the very edge are being pushed away by cosmic expansion. Eventually, they'll cross back over the horizon, their light redshifted into oblivion, disappearing from view forever. The universe is engaged in a cosmic trade, revealing new regions at the same rate it loses old ones. The sphere we can observe is constantly changing, a moving bubble of vision in an infinite sea, Recent simulations suggest that, in the far future, trillions of years from now, accelerating expansion driven by dark energy will push all distant galaxies beyond the cosmic horizon. Future civilizations will look up at the sky and see only their local galaxy group. The rest of the universe will have disappeared beyond the horizon, carried away by expanding space. Those future astronomers, if they exist, won't be able to discover the Big Bang. They won't see the cosmic microwave background. They won't detect Hubble expansion. All the evidence we use to understand the universe will be gone. They'll think their galaxy group is the entire universe, eternal and unchanging. They'll be wrong, but they'll have no way to know it. This creates a disturbing possibility. Might we be in the same situation? Might there be evidence of larger cosmic structures or earlier phases of existence that have already crossed beyond our horizon, leaving us ignorant of the universe's true nature? Some physicists think the answer is yes. The cosmic inflation that happened in the universe's first fraction of a second might have pushed most of the universe beyond our horizon. We might be seeing only a tiny atypical bubble of a much larger and stranger cosmos. There could be regions of space where physical constants are different, where electromagnetism is stronger, where gravity is weaker, where there are additional forces we've never encountered. These regions exist, but they're forever beyond our reach. Or consider this possibility. What if our observable universe is inside a black hole? This isn't as crazy as it sounds. The math of general relativity allows for it. A region of space that appears finite and bounded from the outside could appear infinite and expanding from the inside. Some versions of cosmological models suggest our Big Bang could be the interior of a black hole in a larger parent universe. If true, then asking about the size of our universe becomes meaningless. From our perspective, inside, space extends infinitely. From the outside, we're a finite region of space-time. Both descriptions are valid from different reference frames. And here's the truly wild part. Black holes in our universe might themselves contain entire universes. Every black hole, and there are billions in our galaxy alone, might be a doorway to an infinite expanding cosmos, complete with galaxies, stars, and possibly life. Our universe could be nested inside a black hole, which is inside a universe that's inside another black hole. Ad infinitum. Infinite recursion in both directions. Larger universes containing us, smaller universes contained within us. The physicist Lee Smolin proposed this as cosmological natural selection. Universes that produce more black holes create more baby universes, which inherit slightly mutated physical constants. Over cosmic time, this could lead to universes optimized for black hole production. And what creates lots of black holes? Stars. And what enables stars? The specific values of physical constants in our universe. Our universe might be finely tuned not for life, but for reproduction. It's evolution, but at the scale of universes. And it suggests the answer to how big is the universe might be. It's one of an infinite number of nested universes extending both up and down in scale infinitely. Chapter 13. The Mathematics of Infinity. Okay, we need to talk about infinity more rigorously, because not all infinities are created equal. The mathematician Georg Cantor proved something remarkable in the 1800s. There are different sizes of infinity. Some infinities are literally larger than others. The infinity of counting numbers, 1, 2, 3, 4, is called countable infinity. It's infinite, but you can theoretically list all the members one by one. But the infinity of real numbers, numbers with decimal points, is uncountable infinity. It's a bigger infinity. You cannot list all real numbers even given infinite time. There are more real numbers between 0 and 1 than there are counting numbers in total. Cantor proved this with a diagonal argument that's beautifully simple. Assume you've made a list of all real numbers between 0 and 1. Now create a new number by taking the first digit of the first number, changing it, making that the first digit of your new number. Take the second digit of the second number, change it, make that the second digit of your new number. Continue infinitely. The number you've created differs from every number on your list in at least one position. Therefore, it's not on the list. Therefore, your list is incomplete. Therefore, you cannot list all real numbers. The infinity of real numbers is bigger than the infinity of counting numbers. Mind-blowing? It gets worse. There are infinitely many different sizes of infinity. Each infinity can be used to generate a larger infinity. The hierarchy extends upward forever. Now apply this to cosmology. Is the universe countably infinite or uncountably infinite? Are there a countable infinity of galaxies or an uncountable infinity? Do quantum branches form a countable or uncountable set? The answer affects how we think about probability, quantum mechanics, and the likelihood of anything existing. In a countably infinite universe, you might be able to assign probabilities to events. In an uncountably infinite universe, probability breaks down entirely. Some physicists argue that the universe must be countable, that there's a minimum size to space, the Planck length, and a maximum density of information. This would make the universe large but finite in information content, even if spatially infinite. Others argue quantum mechanics requires uncountable infinity, that wave functions exist in uncountably infinite dimensional Hilbert spaces, and this must reflect physical reality. The difference matters. In a countable universe, your identical copies are rare, scattered across incomprehensible distances. In an uncountable universe, there are uncountably many copies of you in any given volume of space, existing in quantum superposition. Recent work in quantum information theory suggests the universe might be fundamentally discrete, that space and time are quantized at the Planck scale. If true, this would make the universe countably infinite at most, possibly even finite. But other work in quantum gravity suggests space-time might be an emergent property of something more fundamental, and that fundamental substrate might be genuinely continuous and uncountably infinite. We simply don't know yet. The mathematics works either way, but the physical reality, whether infinity is countable or uncountable, remains one of the deepest unsolved questions in physics. Part 3, The Edge of Knowledge, Chapter 14, The Cosmic Web in Unprecedented Detail. Let's ground ourselves back in observable reality for a moment, because even without invoking infinity or multiverses, recent discoveries about the structure we can see are absolutely mind-blowing. In 2021, astronomers completed the Sloan Digital Sky Survey 4, the most comprehensive 3D map of the universe ever created. This survey mapped the positions and distances of millions of galaxies, allowing us to see the cosmic web in unprecedented detail. And what they found was stunning. The universe's structure is far more organized than anyone expected. Galaxies aren't randomly scattered through space. They're arranged in incredibly precise filaments, walls, and nodes, creating patterns that look almost biological. The cosmic web resembles neural networks in the human brain. Seriously. Statistical analyses comparing the distribution of galaxies in the universe to the distribution of neurons in brain tissue show remarkable similarities. Completely different scales. One is nanometers, the other is billions of light years, but the same fundamental patterns. This isn't mysticism, it's mathematics. Both systems are networks optimized for information transfer and efficiency. In the brain, neurons connect to maximize computational power while minimizing wiring length. In the universe, dark matter filaments channel matter along paths of least resistance, creating similar network topologies. Some physicists have speculated that the universe itself might be a kind of computational network, not conscious, but processing information through the interactions of particles and fields. If true, the cosmic web might be the universe's neural architecture, and we're living inside a cosmic computer. Wild? Yes. Unfalsifiable? Maybe. But the structural similarities are undeniable, and they suggest that certain patterns emerge at all scales when systems self-organize. The SDSS-4 also revealed something unexpected: supervoids. These are regions of space with far fewer galaxies than average, and they're huge. The largest known void, the KBC void, is about 2 billion light-years across. If you were in the center of this void, you'd see almost no galaxies in any direction, just empty darkness extending for hundreds of millions of light-years. These voids are so large, they shouldn't exist according to our models of structure formation. Matter hasn't had enough time since the Big Bang to segregate into such extreme concentrations and absences. Their existence suggests either our models are wrong, or something about the universe's initial conditions created seed structures that we don't understand. What's more, recent observations suggest we might be living in a relatively empty region of space. Not a supervoid, but a slight underdensity compared to the cosmic average. This could explain some of the tensions in our measurements of the Hubble constant. If we're in an underdense region, expansion might appear different from here than it would from a more typical location. This is the Copernican principle breaking down. For centuries, we've assumed Earth isn't special. We're not at the center of anything. We're just a random planet in a random location. But what if, by cosmic coincidence, we happen to be in an atypical region of the universe? What if our local environment isn't representative of the cosmic average? If true, this would mean all our measurements and models might need adjustment. We've been extrapolating from our local sample to the entire universe, assuming our neighborhood is typical. If it's not, our understanding of cosmic scale could be significantly off. Chapter 15: Time Dilation and the Relativity of Distance. Here's something that will mess with your concept of size. Distance and time are relative. Thanks to Einstein's relativity, the size of the universe depends on who's measuring it and how fast they're moving. Time dilation is the phenomenon where time passes at different rates depending on velocity and gravity. If you're moving at relativistic speeds, a significant fraction of light speed, time slows down for you relative. to stationary observers. Now imagine a photon, a particle of light. From our perspective, it takes 13.8 billion years for a photon to travel from the edge of the observable universe to us. But from the photon's perspective, 0 time passes. Due to extreme time dilation at light speed, the photon's journey is instantaneous. From the photon's reference frame, the entire universe is contracted to 0 thickness in the direction of travel. Distance becomes meaningless. The universe has no size. This isn't a trick of perception. Both reference frames are equally valid. The universe is 93 billion light-years across from our perspective, and 0 size from the photon's perspective. Both are true simultaneously. This gets weirder when you consider particles traveling close to light speed. Cosmic rays, high-energy particles from space, regularly strike our atmosphere at 99.9999999% the speed of light. From their reference frame, they cross the galaxy in what we would measure as a few seconds, even though, objectively, it takes 100,000 years. There is no objective cosmic clock measuring the true size of the universe. Size is observer-dependent. An alien civilization traveling at near-light speed would measure the universe as dramatically compressed in their direction of travel. From their perspective, crossing the observable universe might take only years of subjective time. This has implications for understanding cosmic scale. When we say the universe is 93 billion light-years across, we're implicitly adopting a specific reference frame, one at rest relative to the cosmic microwave background. Other reference frames would measure different sizes. In fact, there's a theoretical reference frame, the co-moving frame, in which the universe has been the same size since the Big Bang. The expansion we observe is an artifact of our reference frame. From the co-moving perspective, the universe isn't expanding at all. It's always been infinite, and matter is just spreading out within that infinite space. Which perspective is real? They all are. Reality doesn't have a privileged reference frame. The question, how big is the universe, doesn't have a single answer. It depends on the frame of reference you choose. Chapter 16, Black Holes and the Information Paradox. Let's dive deeper into black holes because they fundamentally challenge our understanding of space, time, and the universe's structure. Stephen Hawking proved in the 1970s that black holes aren't truly black. They emit radiation due to quantum effects near the event horizon. This radiation, called Hawking radiation, causes black holes to slowly evaporate over time. But here's the problem. When a black hole evaporates completely, what happens to all the information about the matter that fell in? According to quantum mechanics, information can't be destroyed. It's a fundamental law. But if the black hole evaporates into random thermal radiation, the information seems to disappear. This is the black hole information paradox, and it's been one of the biggest unsolved problems in theoretical physics for 50 years. Recent work suggests the answer might involve the holographic principle we discussed earlier. The information isn't destroyed. It's encoded on the event horizon and eventually re-emitted in the Hawking radiation in a scrambled form. But there's another possibility that relates to cosmic scale. Black holes might be wormholes connecting to other regions of space-time. When matter falls into a black hole, it doesn't disappear. It emerges somewhere else, possibly in another universe entirely. The math of general relativity allows for this. Einstein-Rosen bridges, theoretical wormholes, are valid solutions to the equations. They connect two distant regions of space-time through a shortcut outside normal space. If black holes are wormholes, then the inside of a black hole isn't really inside at all, it's a connection to elsewhere. The singularity at the center might be the other end of the wormhole, potentially billions of light years away, or in another universe entirely. This would mean the universe is more connected than we realize. Black holes wouldn't be dead ends. They'd be tunnels through the cosmic fabric, creating a network of shortcuts through space and possibly between different bubble universes. Some physicists have proposed that entangled particles, quantum particles, linked such that measuring one instantly affects the other regardless of distance, might be connected by microscopic wormholes. Quantum entanglement might literally be tiny Einstein-Rosen bridges, creating instantaneous connections across space. If this ER equals EPR conjecture, Einstein-Rosen equals Einstein-Podolsky-Rosen, is correct, then space isn't fundamental. Distance isn't real. What we perceive as empty space separating particles is actually a network of quantum wormholes creating the illusion of separation. The universe wouldn't be a vast empty expanse with matter scattered through it. It would be a dense network of quantum connections, with space emerging as a collective property of entanglement patterns. This would fundamentally change what we mean by the size of the universe. Size implies separation, distance, empty space between things. But if space emerges from entanglement networks, then asking about size is like asking about the size of a computer program. The question doesn't quite make sense in those terms. Chapter 17, The Simulation Hypothesis. All right, let's address the elephant in the room. What if the universe isn't physical at all? What if we're living in a simulation? Before you roll your eyes, this is a serious philosophical and scientific question that prominent physicists and philosophers take seriously. The simulation hypothesis suggests that our reality is a computational simulation running on some substrate beyond our ability to detect. The argument goes like this. If it's possible to create realistic universe simulations, then advanced civilizations will create many such simulations. There would be far more simulated universes than real ones. Therefore, statistically, we are probably in a simulation. Nick Bostrom formalized this as a trilemma. Either 1. Civilizations never reach the capability to create realistic simulations. 2. Civilizations that reach that capability choose not to create simulations. Or 3. We're almost certainly in a simulation. Since we can't rule out 3, and options 1 and 2 seem arbitrary, the simulation hypothesis remains a possibility. What would this mean for the universe's size? Well, in a simulation, the size of the universe would be determined by computational resources allocated to the simulation. The programmers could make it appear infinite from the inside while using finite computational power. Think about video games. From inside the game world, the environment seems continuous and expansive. But it's actually rendered on demand. Only the parts you're currently observing are computed in detail. The rest exists in low resolution or as placeholder data. The universe might work the same way. What we observe is rendered in high detail. The distant cosmos exists as mathematical descriptions that only get computed when we observe them. This would explain quantum mechanics. The reason particles don't have definite states, until observed is because they literally aren't rendered until observation forces the simulation to compute them. The speed of light might be the maximum processing speed of the simulation. The Planck length might be the pixel size of spacetime. Quantum randomness might be the random number generator. The universe's mathematical nature might reflect the computational substrate it runs on. If we're in a simulation, what exists outside the simulation? A larger universe with different rules, running the computation. And that universe might itself be a simulation in an even larger universe, recursing upward infinitely. Or the simulation might not exist in physical space at all. It might be pure mathematics, a Platonic form instantiated in some abstract computational realm beyond physical existence. This isn't unfalsifiable. Programmer errors, bugs in the simulation code, might appear as physical anomalies. The 2007 discovery of anomalous void structures and the cosmic axis of evil, peculiar alignments in the cosmic microwave background, could theoretically be glitches. Some physicists have proposed experiments to detect simulation artifacts, looking for lattice structures at small scales that would indicate discrete rather than continuous space. So far, no definitive evidence either way. But here's what's really interesting. The simulation hypothesis and the holographic principle might be describing the same thing from different angles. A holographic universe where three-dimensional reality emerges from two-dimensional information is functionally identical to a simulated universe where 3D space emerges from computational processes. The size of the universe in either case becomes a question about information content rather than physical extent. And information content is measured in bits, discrete units that can be counted. Recent calculations based on the holographic principle suggest the observable universe contains about 10 to the power of 120 bits of information. That's a 1 followed by 120 zeros. Enormous but finite. If you had a computer with 10 to the 120 bits of storage, you could theoretically store the complete information content of everything we can observe. Advanced civilizations millions of years ahead of us might build such computers. They might already have done so. We might be running on one right now. Chapter 18, Cyclic Models and Eternal Return. What if the universe doesn't have a beginning? What if the Big Bang wasn't the start of everything, but just one event in an eternal cycle? Cyclic cosmological models propose that the universe goes through repeated cycles of expansion and contraction. The Big Bang was actually a big bounce. The universe contracted to a minimum size, then rebounded into expansion. Before our current expanding phase, there was a previous universe that collapsed. Before that, another expansion and contraction. The cycle repeats infinitely in both directions, eternal past and eternal future. Different models propose different mechanisms. In the ekpyrotic model, our three-dimensional universe is a membrane floating in higher dimensional space. Periodically, our membrane collides with another membrane, creating a Big Bang and resetting the universe. In the conformal cyclic cosmology proposed by Roger Penrose, each cycle of the universe becomes the next cycle's initial conditions. As the universe expands and cools toward heat death, the physics becomes scale invariant. Distances become meaningless. This infinite size cold end state becomes mathematically equivalent to a hot, dense beginning state. The end of one cycle seamlessly becomes the start of the next. These models are testable. They make predictions about patterns in the cosmic microwave background that differ from standard inflation models. Penrose claims to have found evidence of pre-Big Bang black hole collisions, circles of correlated temperature variation that could be imprints from the previous cosmic cycle. Other physicists dispute these findings, but the search continues. If cyclic models are correct, then asking about the beginning or size of the universe becomes meaningless. There is no beginning, there is no end, just eternal cycles of creation and destruction. And here's where it gets really weird. If the universe is eternal and cyclic, and if quantum fluctuations ensure slight variations between cycles, then every possible configuration of matter will eventually occur, not just in parallel universes, but in sequence. Every universe that could exist will exist, not just simultaneously in a multiverse, but consecutively in an eternal series of cycles. This is Nietzsche's eternal return, except it's not philosophy, it's physics. You've lived before, in previous cycles, with slightly different physical constants and histories. You'll live again in future cycles, infinitely many times, with infinitely many variations. Some cycles, atoms never form. Some cycles, life never emerges. But in the cycles where conditions are right, you exist, and you'll exist again and again, forever. The true size of the universe in this model encompasses all cycles, an infinite temporal extent, in addition to potentially infinite spatial extent. Size becomes four-dimensional or even higher if additional dimensions exist. Chapter 19: Extra Dimensions and String Theory. Speaking of additional dimensions, let's talk about string theory and the possibility that the universe has more dimensions than the 3 spatial dimensions we experience. String theory, actually a family of related theories, attempts to unify quantum mechanics and general relativity by proposing that fundamental particles aren't point-like, but tiny vibrating strings. Different vibration modes of these strings correspond to different particles. The math only works if there are extra spatial dimensions beyond the 3 we observe. Most versions of string theory require 10 or 11 total dimensions, 9 or 10 spatial dimensions plus time. Where are these extra dimensions? Why don't we see them? The standard answer is that they're compactified, curled up into incredibly tiny shapes at every point in our familiar 3-dimensional space. Imagine you're an ant on a power line. To you, the world appears one-dimensional, just forward and backward along the wire. But if you were small enough, you'd notice the wire has thickness. There's a second dimension curled around the wire in a tiny circle. That's how extra dimensions might work, curled up so small that only fundamental particles can detect them. The shape of these compactified dimensions is called a Calabi-Yau manifold, and it's complex beyond visualization. But here's what matters. The specific shape of the compact dimensions determines the physics of our 3-dimensional universe. Different Calabi-Yau shapes give different particle masses, different force strengths, different physical laws. String theory doesn't predict one universe. It predicts something like 10 to the power of 500 possible universes, each with different compactification geometry. This is the string theory landscape, and it creates a problem. How do we know which of these 10 to the power of 500 possibilities is our universe? String theory can't currently tell us, but it creates an opportunity. maybe all 10 to the power of 500 possibilities are realized somewhere. In an eternally inflating multiverse, creating bubble universes with different properties, all possible Calabi-Yau shapes might be instantiated somewhere. Our universe has the particular shape it does not because it's the only possibility, but because it's one of countless possibilities. And we exist in this one because it has the right properties for life. This is the anthropic principle on steroids. We observe these physical laws not because they're fundamental, but because we couldn't exist in universes with different laws. Now here's the size implication. If extra dimensions exist, the true size of the universe is measured in all dimensions, not just the 3 we observe. A point in our 3-dimensional space might actually be a 6-dimensional Calabi-Yau manifold. The universe is vastly larger in total dimensional extent than we can perceive. Moreover, some versions of string theory allow for large extra dimensions, dimensions that aren't compactified to microscopic size, but extend macroscopically. These dimensions could be enormous, potentially infinite, existing parallel to our familiar 3 dimensions. We wouldn't see them directly because matter and light are confined to our 3-dimensional membrane, or brain, floating in the higher dimensional space, the bulk. But gravity leaks into extra dimensions, which could explain why gravity is so much weaker than other forces. If large extra dimensions exist, the true universe encompasses all these dimensions. The 3-dimensional universe we observe would be like a page in a book, thin compared to the full extent of the book's 3 dimensions. The total size of reality would include all these parallel brains and the bulk between them. Space would be far more complex and extensive than our ordinary experience suggests. Chapter 20, The Omega Point and the Fate of Everything. Let's fast forward to the end of time. What's the ultimate fate of the universe, and what does it tell us about cosmic scale? Current observations suggest the universe will expand forever, driven by dark energy. Galaxies will move apart, stars will burn out, and eventually, trillions of years from now, the universe will reach a state called heat death. In heat death, all usable energy has been converted to waste heat. No more stars form, black holes evaporate, particles decay into radiation. The temperature of the universe approaches absolute zero. Nothing happens anymore, ever. This is a depressing scenario, but it's what current physics predicts. Unless dark energy behaves differently than we think, or new physics intervenes, heat death is inevitable. But physicist Frank Tipler proposed an alternative, the Omega Point hypothesis. Tipler suggested that if the universe eventually recollapses, which current observations suggest it won't, but bear with me, then in the final moments before the Big Crunch, certain conditions allow for infinite computation. As the universe collapses, time dilation effects near the final singularity become extreme. Observers falling into the crunch would experience time passing slower and slower as measured by external time, approaching infinity. This creates the possibility of infinite subjective time in finite objective time. A collapsing universe could compute infinitely many thoughts, simulate infinitely many experiences, resurrect all possible consciousnesses that ever existed in the final moments before the end. The Omega Point would be a cosmic computer powerful enough to simulate all possible universes, resurrect all possible minds, and achieve a kind of technological godhood in the final instant of cosmic collapse. Tipler suggested this might be the ultimate destiny, that intelligence will spread throughout the universe, convert all matter into computational substrate, and engineer the final collapse to enable infinite computation. The omega point becomes both the end of time and a kind of eternal existence beyond time. This is highly speculative, bordering on theology rather than physics. But it's based on legitimate physics about general relativity and computational limits. Whether it's possible depends on details of how the universe ends. Current observations suggest expansion won't reverse, so the omega point won't happen. But some physicists have proposed alternatives, like the concept of infinite computing in infinite time, if the universe expands forever. If expansion continues forever but slows down asymptotically, the total proper time experienced by observers might be infinite even as coordinate time extends infinitely. This could allow for infinite computation distributed across an eternally expanding universe. Seth Lloyd and others have calculated the computational capacity of the universe. Based on its mass energy content and the laws of thermodynamics, the observable universe has performed roughly 10 to the power of 120 operations since the Big Bang, and contains about 10 to the power of 90 bits of information. If the universe is infinite, these numbers scale up. An infinite universe has infinite computational capacity, potentially enough to simulate every possible configuration of matter, every possible thought, every possible experience. We might already be living in such a simulation, not created by external programmers, but by the universe, computing all possibilities as a natural consequence of its physical laws. Chapter 21. Recent discoveries that shook everything. Let's bring this back to cutting-edge observational science. In just the last few years, several discoveries have fundamentally challenged our understanding of cosmic scale. In 2022, the James Webb Space Telescope began operations, and within months, it found something shocking: massive, mature galaxies in the early universe, far earlier than should be possible according to our models. These galaxies existed only a few 100 million years after the Big Bang. They shouldn't have had time to form. Yet there they are, already containing billions of stars, already structured and evolved. This suggests either our models of galaxy formation are seriously wrong, or there's something about the early universe we don't understand. Maybe structure formed faster than we thought. Maybe there were seed structures from before the Big Bang, imprints from a previous cosmic cycle, or from the larger multiverse. The implications for cosmic scale are significant. If galaxies formed faster than we thought, the universe's evolution might have been different from our models. This affects our calculations of distances, ages, and the overall timeline of cosmic history. In 2023, astronomers announced the discovery of the largest structure ever observed. The Big Ring, a near-perfect ring of galaxies spanning 1.3 billion light-years across. It's so large it challenges the cosmological principle, the assumption that the universe is roughly uniform at large scales. Structures this large shouldn't exist. They violate the theoretical limits on structure size based on the universe's age and the speed at which matter can cluster. Their existence suggests either we're missing something fundamental about structure formation, or the cosmological principle is wrong, and the universe is more varied than we assumed. If the universe varies significantly by region, some areas denser, some areas with different expansion rates, some areas with different structure sizes, then extrapolating from our local observations to the entire cosmos becomes questionable. Also in 2023, astronomers detected gravitational waves from merging supermassive black holes for the first time. These waves have been traveling through space for billions of years, carrying information about cosmic history. By analyzing gravitational wave backgrounds, the combined signal from countless merging black holes across cosmic history, we can map the distribution of matter throughout space and time. This gives us a completely independent way to measure cosmic scale, one that doesn't rely on light. Early results suggest the universe might be slightly more clumpy, matter concentrated in denser regions, than optical surveys indicate. If confirmed, this would affect our understanding of cosmic structure and potentially explain some of the tensions in our cosmological measurements. Chapter 22. What we still don't know. Let's be honest about the limits of our knowledge, because there's a lot we simply don't understand about the universe's true nature and scale. We don't know what dark matter is. It makes up 27% of the universe. Oh, we can detect its gravitational effects, but we have no idea what it's actually made of. Decades of experiments have failed to directly detect dark matter particles. We don't know what dark energy is. It makes up 68% of the universe, and it's pushing space apart faster over time, but we don't know why or how. It might be a property of space itself, or a new field, or a sign our understanding of gravity is wrong. We don't know if the universe is finite or infinite. Our measurements suggest it's flat, which implies infinite, but we can't rule out an incredibly large but finite curved universe beyond our ability to measure. We don't know if there are other universes. The multiverse is predicted by inflation theory and has some indirect evidence, but we can't observe other bubble universes, so it might be unfalsifiable. We don't know what happened before the Big Bang. Some models say nothing. Time itself began at the Big Bang. Others suggest eternal inflation or cyclic cosmology. We have no way to directly test pre-Big Bang scenarios. We don't know why the universe has the specific properties it does. Why these physical constants? Why 3 spatial dimensions? Why does anything exist at all instead of nothing? We don't know if our universe is typical or unusual. If the multiverse exists, ours might be a rare configuration, or it might be average. We have no way to compare. We don't know the ultimate fate of the universe. Current observations suggest eternal expansion and heat death, but dark energy could change behavior. New physics could emerge, or we could be wrong about the expansion rate. We don't know if consciousness plays a role in cosmic scale. Some interpretations of quantum mechanics suggest observation affects reality. If true, the size of the universe might depend on what's being observed. We don't know if we're alone. The vastness of space suggests other intelligent life is likely, but we haven't found any evidence yet. The Fermi paradox, the contradiction between high probability of aliens and lack of evidence, remains unsolved. We don't know if our physical laws are fundamental or emergent. Space, time, matter, energy. These might be approximations of something more fundamental that we don't understand yet. We don't know if mathematics describes the universe or is the universe. Is math a human invention that happens to match reality? Or is reality fundamentally mathematical? These unknowns aren't failures of science, they're frontiers. Each question represents an opportunity for future discoveries that could revolutionize our understanding as dramatically as past discoveries did. Chapter 23: The Technology Revolution in Cosmic Observation. Let's talk about how we're actually measuring all of this, because the story of discovering the universe's true size is inseparable from the story of the incredible technology we've developed to peer into the cosmos. The James Webb Space Telescope, launched in 2021, represents a quantum leap in our observational capabilities. Unlike Hubble, which primarily observes visible light, JWST specializes in infrared, the stretched out light from the most distant objects in the universe. Why infrared? Because of redshift. As the universe expands, light traveling through space gets stretched like a wave on an expanding rubber sheet. Light that started as ultraviolet or visible gets stretched into infrared by the time it reaches us from distant galaxies. The farther away something is, the more red-shifted it becomes. JWST can see galaxies that formed only 200 million years after the Big Bang, galaxies whose light has been traveling toward us for over 13.6 billion years. But here's the crazy part. Those galaxies aren't 13.6 billion light-years away anymore. Due to cosmic expansion, they're now roughly 46 billion light-years away. We're seeing them as they were billions of years ago, but they've been moving away from us this whole time. This time delay is built into every observation we make. When we look at distant objects, we're not seeing the universe as it is. We're seeing a historical record. The farther we look, the further back in time we see. Our observable universe is essentially a giant light cone extending backward in time, with the cosmic microwave background forming the surface of last scattering, the earliest light we can observe. JWST has already forced us to reconsider galaxy formation timelines. The mature galaxies it found in the early universe shouldn't exist according to hierarchical structure, formation models which predict small structures forming first and gradually merging into larger ones. But what if structure formation wasn't purely hierarchical? What if there were primordial density fluctuations, regions of slightly higher density seeded during inflation, that allowed some regions to collapse into galaxies faster than others? Recent analyses of JWST data suggest this might be the case. The early universe might have been lumpier than we thought, with stronger density contrasts allowing rapid galaxy formation in certain regions. This would explain the unexpected observations without requiring us to throw out our entire cosmological framework. Beyond JWST, new observatories are coming online that will revolutionize our understanding of cosmic scale. The Vera Rubin Observatory, set to begin operations soon, will survey the entire visible sky every few nights, creating a time-lapse movie of the universe. It will detect billions of galaxies, track moving objects, and find transient events like supernova and colliding black holes. The sheer data volume will be staggering, about 20 terabytes per night, over 500 petabytes over 10 years. Machine learning algorithms will sift through this data looking for anomalies, unexpected structures, and new phenomena we haven't even imagined yet. The Square Kilometer Array, currently under construction, will be the world's largest radio telescope network. With a collecting area of 1 square kilometer spread across thousands of individual antennas, it will map the distribution of hydrogen gas throughout cosmic history. Hydrogen is everywhere in the universe, and by mapping its distribution, we can trace the cosmic web in unprecedented detail. We'll see how matter flowed along dark matter filaments, how galaxies formed at the intersections of these filaments, and how the large-scale structure evolved over billions of years. These observations will test our models of cosmic structure formation at scales and resolutions never before possible. If we find structures larger than our models allow, or if matter distribution doesn't match predictions, we'll need to fundamentally rethink our understanding of cosmology. Chapter 24: Gravitational Wave, Astronomy and Ripples in Spacetime. Gravitational waves, ripples in spacetime itself, have opened an entirely new way of observing the universe. Unlike light, which can be absorbed, scattered, or blocked, gravitational waves pass through everything essentially unimpeded. When LIGO, Laser Interferometer Gravitational Wave Observatory, first detected gravitational waves in 2015, it was from 2 black holes spiraling into each other 1.3 billion light-years away. The waves stretched and squeezed space itself by less than 1,000th the width of a proton as they passed through Earth. The fact that we can detect this is a testament to the incredible precision of modern physics. Since then, we've detected dozens of black hole mergers, neutron-star collisions, and potentially other exotic events. Each detection gives us information about massive objects across cosmic distances in ways light cannot. But the real revolution is coming with space-based gravitational wave observatories. LISA, Laser Interferometer Space Antenna, planned for launch in the 2030s, will consist of 3 spacecraft flying in formation millions of kilometers apart, detecting gravitational waves with much longer wavelengths than LIGO can observe. LISA will detect supermassive black hole mergers, events so energetic they shake the fabric of space-time across entire galaxies. These mergers happen when galaxies collide, bringing their central supermassive black holes together in a death spiral, lasting millions of years before the final merger. By observing these mergers throughout cosmic history, we can map how galaxies evolved, how often they collided, and how the universe's structure developed over time. Gravitational waves carry information from epochs and environments where electromagnetic radiation can't reach us. Even more exciting, gravitational waves from the Big Bang itself might be detectable. Cosmic inflation should have produced a background of gravitational waves, and detecting this primordial gravitational wave background would be direct evidence of inflation and give us information about the universe's first fraction of a second. The Nanograv collaboration recently announced evidence of a gravitational wave background, a persistent hum of gravitational waves filling the universe. This background likely comes from countless supermassive black hole mergers happening throughout cosmic history, their waves overlapping to create a persistent signal. By analyzing this background, we can infer the total number and masses of merging black holes across cosmic time, giving us an independent measure of cosmic structure formation. It's like hearing the collective sound of the universe's largest objects crashing together over billions of years. Chapter 25: dark matter's hidden architecture? We know dark matter exists because we can see its gravitational effects on visible matter and light. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than we can account for. Gravitational lensing, the bending of light around massive objects, reveals invisible mass throughout the universe. But we still don't know what dark matter is made of. Candidates include WIMPs, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and more exotic possibilities. Decades of experiments have searched for direct detection of dark matter particles with no confirmed discoveries yet. However, recent simulations of how dark matter behaves on cosmic scales have revealed something fascinating. Dark matter doesn't just exist as diffuse halos around galaxies. It forms an intricate cosmic web of filaments, sheets, and nodes at all scales. The Illustries and Eagle simulations, massive computational projects modeling the evolution of the universe, show dark matter forming structures that look remarkably similar to biological networks. Filaments connect galaxy clusters like neurons connected by axons. Matter flows along these filaments like information flowing through neural pathways. At smaller scales, dark matter forms subhalos within larger halos, smaller clumps of dark matter orbiting within galaxy halos like moons orbiting a planet. Our Milky Way might contain hundreds or thousands of these dark matter subhalos, each potentially capable of trapping normal matter and forming dwarf galaxies. Some of these subhalos might exist without any visible stars at all, dark galaxies made entirely of dark matter, invisible except for their gravitational influence. Recent observations have found anomalous gravitational lensing that might be from these dark galaxies. The total mass in dark matter is about 5 times the mass in normal matter. This means the real structure of the universe, the scaffolding on which galaxies form, is invisible to us. Everything we see is just decoration on an invisible framework we can only detect indirectly. If we could see dark matter, the universe would look completely different. The familiar galaxies and stars would be tiny bright spots embedded in vast dark matter structures. The cosmic web would be visible in all its complexity, with matter concentrated along filaments connecting enormous nodes where galaxy clusters form. Recent proposals suggest we might eventually be able to see dark matter indirectly through its effects on the cosmic microwave background. As CMB photons pass through dark matter structures, they get slightly deflected, creating distortions in the CMB temperature map. By analyzing these distortions, we might be able to map dark matter distribution throughout cosmic history. This would give us the first direct visualization of the universe's dark matter skeleton, the hidden architecture on which everything we see is built. Chapter 26: The Cosmological Constant Problem and Vacuum Energy. Let's talk about one of the biggest unsolved problems in physics, the cosmological constant problem. It's directly relevant to understanding the universe's size because it involves the energy of empty space itself. Quantum field theory predicts that empty space isn't actually empty. It's filled with virtual particles constantly popping into and out of existence, creating a background energy density called vacuum energy. This energy should contribute to the cosmological constant, the term in Einstein's equations corresponding to dark energy. But here's the problem. When you calculate the expected vacuum energy using quantum field theory, you get a number that's about 10 to the power of 120 times larger than the observed value of dark energy. This isn't just being wrong by a few percent. This is being wrong by 120 orders of magnitude. It's possibly the worst prediction in the history of physics. If vacuum energy were actually as large as quantum field theory predicts, the universe would be expanding so fast that atoms couldn't form. Space would be ripping itself apart faster than gravity could pull anything together. The fact that we exist proves the calculation is wrong, but we don't know why. This suggests we're missing something fundamental about how quantum mechanics and gravity interact at cosmic scales. Some physicists think there's a mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe. But we don't know what that mechanism is. Others think the vacuum energy actually is enormous, but it's balanced by some unknown negative energy term, leaving only a small residual. The fine-tuning required for this cancellation would be extraordinary, like balancing a pencil on its point to within 1 part in 10 to the power of 120. The anthropic principle offers an explanation. In a multiverse, with different values of vacuum energy in different regions, only regions with small vacuum energy allow galaxies and life to form. We observe a small cosmological constant because we couldn't exist anywhere else. This is philosophically unsatisfying, but might be correct. The universe's properties might not have a deep fundamental explanation. They just are what they are, because those are the properties that allow observers to exist. Recent theoretical work suggests vacuum energy might not be constant after all. It might vary with time or location, which would explain both the cosmological constant problem and some of the tensions in our cosmological measurements. If vacuum energy changes over cosmic time, the expansion rate would also change in unexpected ways. This could explain the Hubble tension, the discrepancy between local and distant measurements of expansion. Different eras of cosmic history might have had different vacuum energy densities, affecting how we interpret observations. Chapter 27, The Information Content of the Universe. Let's get really fundamental and ask, how much information does the universe contain? Information, in the physics sense, is measured in bits, binary digits that can be 0 or 1. Every particle, every field, every quantum state represents information. The total information content of the universe is a measure of its complexity. Based on the holographic principle, the maximum information content of any region of space is proportional to the area of its boundary, not its volume. For a sphere, information scales as radius squared, not radius cubed. For the observable universe, this gives us an information content of about 10 to the power of 120 bits. That's the total information needed to completely specify the quantum state of everything we can observe. But there's a catch. Quantum mechanics tells us we can never actually measure all this information. The Heisenberg uncertainty principle limits how precisely we can know certain pairs of properties simultaneously. Measuring one quantum state affects others. Perfect information is impossible. The universe itself might not know its complete state. Information might be fundamentally limited, not just by our measurement capabilities, but by the structure of reality itself. Recent work in quantum information theory has shown that entanglement, the spooky quantum connection between particles, contributes to the universe's information content in unexpected ways. Two entangled particles share information that can't be assigned to either particle individually. If the universe is highly entangled, which quantum field theory suggests it is, then the information content might be much larger than naive counting would suggest. Entanglement creates correlations that increase total information. Some physicists think entanglement might be the fundamental stuff the universe is made of. Space, time, matter, and energy might all emerge from patterns of quantum entanglement. Information would be the only truly fundamental thing. This view is supported by the ER equals EPR conjecture we mentioned earlier, the idea that quantum entanglement creates microscopic wormholes connecting distant particles. If space emerges from entanglement networks, then asking about the size of the universe becomes a question about information topology rather than geometric distance. The universe might be fundamentally discrete, made of irreducible bits of information with no continuous substrate. Space and time might be approximations that emerge at large scales from underlying quantum information. If true, the universe's size would be measured in the number of information processing elements and their connection topology, not in meters or light years. Distance would be derivative, emergent, not fundamental. This completely changes what we mean by cosmic scale. The question, how big is the universe, becomes, how much information does the universe process, and how is that information connected? Chapter 28, The Future of Cosmic Discovery. Where do we go from here? What discoveries await us in the next decades of cosmic observation and theory? Several major experiments coming online in the 2020s and 2030s will revolutionize our understanding. The extremely large telescope in Chile, with a 39-meter mirror, will be the largest optical telescope ever built. It will see first-light galaxies, characterize exoplanet atmospheres, and observe the universe with unprecedented resolution. The Nancy Grace Roman Space Telescope will map the sky in infrared with a field of view 100 times larger than Hubble, finding thousands of exoplanets and creating detailed maps of dark matter distribution through gravitational lensing. CMBS-4, a next-generation cosmic microwave background observatory, will measure the CMB with exquisite precision, potentially detecting primordial gravitational waves from inflation and mapping the universe's earliest moments. The Hydrogen Epoch of Ionization Array, HERA, will observe the period when the first stars turned on, ionizing hydrogen gas throughout the universe. This era, about 100 to 500 million years after the Big Bang, represents a major phase transition in cosmic history. These instruments will answer current questions and undoubtedly raise new ones. Each major advance in observational capability has revealed unexpected phenomena: quasars, gamma-ray bursts, dark energy, fast radio bursts. What will we discover next? Some physicists expect we'll find evidence for or against the multiverse in detailed CMB measurements. Others think we'll detect dark matter particles directly in underground experiments. Some anticipate discovering new fundamental particles or forces through cosmic ray observations or particle collider experiments. Theoretical physics is also advancing rapidly. Quantum computing might allow us to simulate quantum field theory and quantum gravity in ways impossible with classical computers, revealing new insights into fundamental physics. Machine learning algorithms are already finding patterns in astronomical data that humans would miss. As data sets grow larger and algorithms grow more sophisticated, AI might discover new cosmic structures, new physical relationships, or new anomalies requiring explanation. The next decades will also see advances in space exploration. The Artemis program aims to establish a permanent human presence on the Moon, creating a platform for deeper space exploration. Mars missions might discover evidence of past life, answering one of humanity's oldest questions. Are we alone? The search for extraterrestrial intelligence continues expanding, with new radio telescope arrays and optical SETI programs scanning millions of stars for signs of artificial signals. The discovery of even microbial life elsewhere would profoundly impact our understanding of life's frequency in the universe. If the universe is infinite and filled with infinite planets, then life almost certainly exists elsewhere. But the Fermi paradox, the apparent absence of detectable alien civilizations, suggests either life is rare, intelligent life is rare, or technological civilizations don't last long. Answering these questions will help us understand our place in the cosmic scale. Are we a common outcome of physical laws, or an improbable accident in an infinite sea of sterile worlds? Chapter 29: Philosophical Implications of Cosmic Scale. Let's step back from the physics and consider what all this means philosophically and existentially. The universe's incomprehensible scale fundamentally changes how we think about meaning, purpose, and significance. In a universe with trillions of galaxies, each with hundreds of billions of stars, many with planets, the statistical likelihood of countless other civilizations becomes overwhelming. Yet we've found no evidence of alien intelligence. This suggests either we're early, among the first civilizations to arise, or civilizations don't last long, or we're fundamentally wrong about life's probability. The possibility of an infinite universe creates stranger implications. In an infinite universe with infinite time, everything that can happen will happen, infinitely many times. There's no such thing as a unique event. Every moment you experience has occurred infinitely many times before and will occur infinitely many times again. This challenges concepts of individuality and uniqueness. You are not unique. There are infinitely many versions of you having this exact experience right now in distant regions beyond the cosmic horizon. Free will becomes questionable in such a universe. If every possible choice you could make is realized somewhere, in some branch or region, then the choice becomes which universe you happen to be in, not what you decide. Some philosophers argue this makes morality and meaning impossible. If everything happens everywhere, nothing matters. Others argue the opposite. Meaning is local. What happens in this universe to these people in this moment matters intrinsically, regardless of what happens elsewhere. The cosmic perspective can be either terrifying or liberating. Terrifying because it reveals our cosmic insignificance. We're atoms on a rock orbiting an average star in an unremarkable galaxy in an unimportant region of an infinite universe that doesn't care about us. But liberating because it frees us from cosmic narcissism. The universe doesn't revolve around us, and that's okay. We create our own meaning through our choices, relationships, and actions. Significance is something we make, not something granted by cosmic importance. Carl Sagan's pale blue dot speech captures this duality. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. Our cosmic insignificance is precisely what makes our choices significant. In an uncaring universe, the care we show each other is the only care that exists. Meaning isn't diminished by cosmic scale. It's all the more precious because it's fragile and temporary. The realization that we're made of atoms forged in stellar explosions, that we're the universe's way of knowing itself, that consciousness emerged from quantum fields and space-time geometry. This should inspire awe, not despair. We are, as physicist Lawrence Krauss put it, star stuff contemplating the stars. The universe created us as a way to understand itself. Our questions about cosmic scale are the cosmos asking questions about its own nature. Conclusion. So, what is the true size of the universe? Here's what we know for certain. The observable universe is 93 billion light-years across, containing roughly 2 trillion galaxies, each with hundreds of billions of stars. This alone is almost incomprehensibly vast, but recent discoveries suggest this observable sphere is just the beginning. The universe appears to be flat, which mathematically implies it's likely infinite in extent. Beyond our cosmic horizon lie infinite galaxies, infinite stars, infinite possibilities. Cosmic inflation predicts our observable universe is one bubble in an eternally inflating multiverse, with countless other bubble universes, each potentially infinite, each potentially with different physical laws. Quantum mechanics suggests every quantum event spawns branching timelines, creating an infinite multiverse of possibilities, all playing out simultaneously. String theory allows for 10 to the power of 500 different possible universes with different dimensional geometries, potentially all realized somewhere in a vast multiverse landscape. The holographic principle suggests our three-dimensional space might be a projection from information encoded on a two-dimensional boundary, fundamentally changing what we mean by size. Cyclic cosmological models propose an eternal sequence of universes before and after ours, extending infinitely in time. Extra dimensions could exist, making the total extent of reality vastly larger than our three-dimensional perception reveals. The truth is, we've only recently begun to comprehend just how little we understand about cosmic scale. Every discovery seems to reveal that the universe is larger, more complex, more strange than we imagined. The true size of the universe depends on what you include. Just the observable portion? 93 billion light-years. The total physical universe, if it's infinite? Literally infinite. The multiverse of all possible bubble universes? Infinitely infinite. All quantum branches? Uncountably infinite. The full dimensional extent including compactified and large extra dimensions? Beyond our ability to conceptualize. We've discovered that the universe is almost certainly far larger than our ancestors imagined. Larger than what we can see? Possibly infinite? Possibly part of a multiverse that makes our infinity seem small by comparison. And perhaps most humbling, we may never know the complete answer. Some aspects of cosmic scale might be forever beyond our ability to measure or observe. The ultimate truth about the universe's size might remain one of existence's deepest mysteries. But that's what makes this so exciting. Every new telescope, every new theory, every new discovery brings us closer to understanding We've come so far, from thinking the stars were a few thousand miles up to measuring structures billions of light years across. Who knows what we'll discover next? The universe is vast beyond comprehension, and it's probably far, far vaster than even that. Look up at the sky tonight. Those stars you see? They're just the nearest few thousand in our tiny corner of one galaxy among trillions. And that's just what we can observe in our local bubble of an possibly infinite universe that might itself be one of infinite universes in dimensions we can't perceive. You are made of atoms forged in stellar explosions billions of years ago, living on a tiny rock orbiting an average star in an unremarkable galaxy in a universe of incomprehensible scale. And somehow, despite all that vastness, you exist. Right here, right now, conscious and aware and contemplating it all. That's the real miracle. Not just that the universe is unimaginably large, but that we, tiny, brief, improbable, are here to witness it and try to understand it. We've just begun to discover the true size of the universe, and it's magnificent,